info and extra tools that you can use when we're trying to solve these types of problems. Before we do that, let's look at the work that we've got so far in Unit 6. Sorry, I can't get this bar out of the way, I don't think. So here's my layout of Unit 6. Here, let me hide this taskbar. I don't know why this, there we go. So I realized that when you open up Edmentum, it looks a little different than this, but the layout is the same. So Unit 6, these are the lessons, the tutorial lessons. Dilations, this is what we did on Monday. Tuesday. For now, I skipped the course activity. We then, on Wednesday yesterday, we did this. And actually, it's what we're going to continue more of today. And then next week, I think we're going to circle back and do this course activity. And then we'll be testing next week on everything from Unit 6. It's a pretty short unit. So we can have this unit done on Tuesday or maybe Wednesday if we stop for a review day, which I think we should do. So that's our plan for the next week. We've already covered properties of dilations, so we should have this mastery test done. And then we covered similarity and similarity transformations, and that was the second mastery test. And then today we'll be finishing this third lesson. So we're going to do this test together as a group. We're going to start it together after we add on another concept. And then next week, we'll take care of this course activity because they're actually teaching some new information in the course activity, kind of like a tutorial. So we're gonna cover that material next week, and then we'll review and we'll have a test. Any questions on the schedule? Concerns? All right, no questions or concerns. If you want to write this down or take a picture, please do so. This is our plan for the next week. We'll be finishing Unit 6 up. I'm planning for Wednesday to have it finished. Testing on Wednesday next week. All right. So what I want to do today is just finish yesterday's lesson, and we're going to expand on one of those concepts that came up during class. So this is the third tutorial. Again, but we're finishing it and just adding a little to it. So today we'll be looking at writing proportions to solve the triangle problems. I've been focusing on finding the scale factor in solving our triangle problems like that. So think of this approach that we're going to look at now. Think of this as an alternative to solving for scale factor when we're trying to find missing parts of triangles, missing side lengths or sections of a side length. Think of it as an alternative way. Now, sometimes though, we will have to. Some questions will require us to write the proportion. So if sometimes it'll be an alternative, and then sometimes it is going to be like the requirement, where scale factor won't help us quite as well as being able to do these proportions. That's my plan for now. So this is probably not going to be a whole hour. This should be like 20 minutes, and then we're going to stop and go through the mastery test individually, but as a group, so that I can help you with any questions while you're doing it. Okay, we looked at our calendar already. So I wanted to start this talk about proportions and link it to what we've been doing this whole week with scale factor and with dilated figures. So let's start with a simple example like we've been using. So let's say we had our right triangle. I've used a similar example to this all week. Let's say we had a 3, 4, 5 right triangle, and then we dilated it using a scale factor. Let's say we did times 3. So a 3 times bigger triangle. I'm going to put it below here. Just bear with me. Assume that the scale is proper. So if I multiply all the original sides by 3, we're scaling this thing up 3 times bigger. We'll have a 9, 12, 15. Awesome. Good job, Antonio. Thank you. Now, where does proportion fit into this? So far, I'm just talking about scale factor. Let me put that vocab up here. 3 scale factor. So scale factor and proportion go hand in hand, but I've been focusing maybe a little too hard on just scale factor. So where proportion fits into this, I'm going to change my color quick to yellow. It's writing two equal fractions, equal proportions that are equal to each other based on the two triangles. And here's what I mean. The way I've positioned these two triangles, you can maybe see it as a left side. That's 3 and 9. Those are the left side. Let me label that. They each have a left side. They each have a bottom side. So here we have bottom side is the 5 and the 15. And then you see the right side of the triangles as well, 4 and 12. I'm just going to label all parts here. So we can set up an equality of proportions whenever we have these similar triangles or dilated triangles. And we can use this proportion to help solve for unknowns. And we'll do a problem like that in just a second. How we're going to set them up is along these lines. So you can say left side over left side. So what I mean by that is left side of the first triangle over left side of the second. This is equal to the bottom of the first triangle, bottom side rather, you know what I mean, to the bottom of the second. We could also use the right side to right side if we wanted to. So think of this as some examples of how to start proportions. We'll look at the numbers and see why this works, see why this is true. Proportions. So let's try it with left side, bottom side, bottom side. So for instance, the left side of our small triangle was 3. Left side of the new version, the dilated, is 9. And then bottom side of the first small triangle was 5. Over bottom of the new one is 15. So I'm saying these two fractions are equal. Is that true? 3/9 is equal to 5/15. Is that true? And how can we tell if it's true or not? Any ideas on how to tell if that's a true statement that I just wrote down? 3/9 equals 5/15.
Because they're just dilated, but it's the same side.
These fractions you could almost think of as dilated. Yeah. If we, let's see, reduce the fractions, we might see some of this truth emerge from this situation. So let's say 3/9, we try to reduce that. We could divide the top by 3 and the bottom number 9 by 3. So dividing by 3 on both sides here to reduce the fraction, that's 1 over 3. Can I divide 5/15 by 3 and 3? I can't because 5 doesn't divide evenly by 3, but we can reduce 5/15 by dividing both of these guys by 5. And then what do we get? We get 1 over 3. So we set up this proportion statement, this equation. Left side over left side equals bottom over bottom. And it's a true statement. It's true when we reduce the fractions because they're proportional. So if the triangles weren't similar, if they weren't actually a dilation of one of the other, then this wouldn't work. Because we're living in a world this week of dilated figures and proportional figures, like we're purposely making one bigger than the other by timesing by 3, then we get this ability to make these proportions. If we had chosen the right side, instead of like left or bottom, that'll work too. How we're going to use this as a tool is to solve for unknowns, just like we were doing in some of yesterday's examples. I'm going to move on, but I'll wait a few moments if people are still writing down. I'm sorry about this bar. I can't get it out of the way. Oh, maybe I can. Sweet. Okay, I can't see if anyone is putting anything in the comments right now. So just please turn on your mic and let me know if you want me to see a comment or anything. Let me also circle what I really want you to. I mean, this whole page is important. This whole page you should have for reference. But make sure to have this part, if nothing else. Examples of proportions is writing it like this. The order matters. So when we started our proportion, left side on top, that was my like beginning triangle or my smaller one, right? And then below it's left side of the second dilated version. Make sure to do the next fraction in the same order. So if you have like original or starting on top and then you're like new dilated on the bottom, make sure that the second one you make is also in that same order. Otherwise, we're basically mixing it up. So this should be original and then the bottom should be the new dilated version again. So as long as you're consistent with how you're setting up the proportion, it'll always work. Let's try solving an actual problem with this. Yesterday, before I do that, hang on. I'll try one more thing. Sorry, I was not prepared, I guess. I thought I had a different example ready to go. Uh, let's see. Let's try this one. We did this example yesterday using scale factor. Now what we're going to do is try solving the same problem, but using the proportion idea instead. Cool. Okay, sorry about that wait. Okay, let's get back to it. So this should look familiar to what we did yesterday. I'm going to start by calling our question mark x because we're going to be solving for that like side right here. And it's usually better to use a variable than a question mark. It can just get a little weird. So how do we solve this problem using proportions? I still want to separate them out. If not on paper, then at least in my mind's eye. We want to do our best to separate the two triangles. So you should see a small inner triangle. I'm going to highlight that right here. So let's pull that out and then label the sides properly. Here's my small. And then next to that is our larger whole triangle that reaches all the way to like the very top of the image and all the way to the far right of the image. All the way down there. So pull out the larger looking triangle. I want to encourage you guys to do this on paper just to keep track of your work. Now we can label the sides properly. So for my small triangle, left side is 20, bottom is x. That's our unknown. Now for the larger side, we've got 28, and on the bottom is x plus 18. just so we are clear, this 18 is only representing that little stretch. That's why I'm saying it's x for the unknown plus the 18. And now we can use the idea of proportions to solve this, and we're actually going to skip using scale factor entirely. So I realized we solved this yesterday using scale factor. I wanted you to see you could also use the proportion way to do it. So here we go. Let's do left over left equals bottom over bottom. And we'll have an equation then that will solve for x. So left for my small is 20, is to or over 28 equals bottom of the first triangle is x over bottom of the new triangle or bigger one is x plus 18. So this is the same setup that we just did on that first example. We've got left over left equals bottom over bottom. We're not using right sides because there's no information about the right side. There's nothing there. So it's like unusable to us, right? So we have to work within the confines of whatever they give us. If they give you left and bottom, bottom, use that. Maybe it'll be right eventually. You'll use the right sides then if they give you numbers for those. Okay, so I think the fastest way to do this problem is to use what's it called? Cross multiplying. We're essentially multiplying both sides by 28, and on the left they cancel. And then we're going to multiply both sides by this whole expression in the denominator, x plus 18. So we're cross multiplying. X plus 18 is multiplied to the 20. And then 28 is multiplied across to x. So no more fractions. Very nice. We do have to distribute 20 times everything in that parentheses. So we have 20x plus whatever 20 times 18 is. 360. Let me double check. Yes, 360. Okay, equals 28x. We've just got a simple like equation now solving for x. So we want to combine like terms. So minus 20x on both sides. And now divide both sides by 8. 45 is equal to x. So see how this is an alternative to what we did with scale factor. We could use scale factor to solve this problem, but proportions are another useful tool. The scale factor is kind of hidden in the problem, but we're not solving it that way. Any questions or concerns so far on this idea of proportions? Writing the two equal fractions and then solving for the unknown part, please. Any questions on how I set up those two triangles, the 20 and x or the 28 and x plus 18 at the beginning? No. Okay, let's practice before we finish this. I want to show you writing the proportions when we don't get the numbers for the sides, but everything is labeled. I know yesterday there was some hesitation with naming the triangles. This kind of goes with that. It's practice naming your triangles and practice identifying side lengths. So here's an example, another triangle being cut across. And if we assume that these two are parallel, that means the triangles we're looking at are all proportional to each other. So we can use the scale factor or use proportion to solve problems with it. So let's separate them out. like we've been doing. So cut out the top smaller looking triangle, this guy right here. So what should be the 3 points? If this is my top one, I'm pulling out to the left. What should be the 3 points that compose its like edges, its vertices, its points? We see A is the top one. What are the two on the sides? Yeah, thank you. DE, for sure. And then let's look at our larger one. We kind of separate that out on its own. And now this is A, B, C. A, B, C. I want to just practice writing the proportions with you guys in this like theoretical way. It's left over left equals bottom over bottom. And then we can do right versions too. Right over right equals left over left. So let's try this. AD is to left side of the bigger one, AB. So that's like left over left here. And let's try right over right. So then that would be equal to AE over AC. That's doing left, left, right, right. Think about it as like a mix and match. You can write all of the different sides compared to each other. How we'll choose what to use is what parts in the problems we're given have actual like information. Let's try another one. So like bottom, start with that one. Bottom over bottom. So that'll be DE is 2 over BC. And we could say right, right again. AE is to AC. That's how we name those sides. So if you were given triangles where instead of dealing with it as like numbers, they're just labeling the sides, we could still set up our proportions as long as we know the triangles are similar. As long as we know that they are, one is a dilation of the other, they're proportional. All right, it's 10:25. I've got some of the questions from the mastery test ready to go here. This is for the third mastery test called Similarity, Proportions, and Triangle.